Hi, everybody. I'm here to give you a very quick Xen update, and then I'm going to follow up with some information about a new project based on Xen for Edge and IoT. Compared to a couple of years ago, when we started seeing Xen actually being deployed in production in IoT and embedded devices, we have a far better idea of what are the key features and requirements that we need to meet to make Xen a viable solution. And I think the first and foremost is probably real-time. And when I say real-time, I mean low and deterministic RQ latency. The second point, which is very important, it's short boot times, because these are, after all, embedded devices. So when you click power on, you want it to be on, right? You don't want to wait seconds, minutes for it to boot. Device virtualization is a long and complex topic, because you need to be able to assign devices to VM, also share devices with multiple VMs, do both at the same time, assign a device and then share it with multiple VMs. So we do driver domains that way. And also there is VM-to-VM communication mechanism. And finally, is also becoming increasingly important to work on a certifiable code base. Many of the IoT and embedded scenarios where an hypervisor is needed require certifications. So I'm here to tell you that actually we made progress recently on all of these major areas. The first area is static partitioning. So it has always been possible to get the configuration where each virtual CPU run on a separate physical CPU. And that is the best to minimize RQ latency, so there is no scheduling involved. It used to be possible, but complex. You have to do vCPU pinning by hand. It was difficult. Now, you can do that out of the box by passing sched equal null, VWFI equal native, give you an out-of-the-box static partitioning configuration with minimal RQ latency. And on Xilinx and PSoC system is 2.5 microsecond. So it's only one command line option, two command line options away. The other area where we did improvements is VM-to-VM communications. Again, it has always been the case that there were a number of ways to communicate between VMs. These are only three of the most common. libvchan is the one used by the CubeOS project. It's a way to set up a shared page between VMs. PV calls is a strange new networking paradigm that can be used to communicate across VMs. And V4V is based on a hypercode to copy of data. But the point is now we have one more. And this is a way to set up a shared memory region across multiple VMs directly from the config file. The benefit of this is you need no Xen support whatsoever inside your guest to be able to use it. As a matter of fact, you can use it, for example, to set up a shared memory area and use OpenAMP RP message specifically to communicate across VMs. This is going to be upstream and available most likely in the next Xen release. And then we are working to reduce the code size and trying a path towards certifications. So the Xenon ARM code base was already far smaller than the Xenon x86 code base, but we enhanced the kconfig architecture to come up with even smaller code sizes. And is now, as you see the number there, it's 46,000. This is for NPSoC, Xilinx NPSoC configuration, which is lower than 50,000. That is a rule of thumb, which the threshold you need to be below to make it certifiable. The other thing we are doing is we are working with PRQA. PRQA are a provider of very complex tools to do analysis of violations for code style and other requirements for certifications. So we have access, key member of the community, to have access to this tool, and my plan is slowly to grind through them from the most important, from the most severe to the less severe, and move forward to get a code base that is easier to certify. There are also discussions about actually do the certification within the Xen project, but they're at the stage of ideas at the moment, because being an open source project on Linux Foundation is new territory. But I think the most interesting feature that I'm going to talk to you about today is dom0less. So dom0less is a way to run directly multiple VMs from Xen. So it used to be the case that you have to boot Xen, dom0 kernel, dom0 user space, then you use Excel, and you start a second VM. It's not exactly a quick boot path, is it? If you remember the points, the major area we wanted to improve is short boot times, is one of them. And this gives you exactly that, because it allows Xen to boot in parallel multiple VMs, so dom0, and in this example, 2 more VMs on different physical cores. So the boot time goes from 10 seconds to 1 second, basically. So I'm going to, so the idea is Xen, you boot loads in memory, the kernel and RAM disk, and Xen does the parallel boot. Do you see this? Yes. So I'll reboot the Xilinx MPSoC board where I configured the system for dom0less, and is loading using TFTP, Xen, and the kernels. Now you see a lot of messages. Here are all the domains booting in parallel, and that's it. dom1 and dom2 have already completed the boot sequence because they're tiny busybox-based guests. dom0 is still booting now. Now we see that there are, in fact, 3 domains running, dom0, dom1, and dom2. The other 2 don't even have a name at this point. The other thing I want to show you is, you see here, dom0 doesn't have networking. That's because I assigned the network card to one of the other domains. So I'm switching input to dom1 here, and you see the network is there and working. So if you're interested about this, I can give you a lot more details. And I can show you how the parameters are passed. They're all based on device tree. We have extended the existing multi-boot specification that is device tree based to pass information about these other additional VMs and their parameters. OK. So yes, so feel free to reach out to me. I'm here until Friday. I'm happy to deep dive into these topics and more. The next thing I want to talk to you about is a new experimental project, sub-project, actually, of Xen Project in the Linux Foundation. So the problem here that we are trying to solve is, well, in many IoT use cases, especially the one we call edge nowadays, we have the issue of needing to deploy at runtime multiple applications and manage their updates independently. So we want to be able to install it at runtime and then update separately from the system, for example. So here is an idea. Why don't we use Docker? Which is a fair idea, because Docker actually comes with the tools to do the packaging, contains all the dependencies of these applications, comes with a delivery mechanism to deliver the application to the target, and a way to update the apps as well. So it's actually a good place to start. Now, when we talk about Docker, and especially in containers, we have to keep in mind, though, that we are talking about a couple of different things. So one thing is the image format specification, the packaging itself. In a way, the new RPM, okay, or DEB, or anything. The other thing we are talking about, which in fact is covered by a separate specification, is about the way we run it. And the separation is made very clear in Docker today with container D and runc, one binary, and project, well, sub-project, deal with the packaging, and the runtime is dealt by runc. So why I'm telling you this? Because the packaging is great and can pretty much be used everywhere, from the tiniest embedded board to the largest HPC system. As a matter of fact, with Singularity, it is used on HPC. But the runtime environment is not actually kind of well suited for all scenarios. It's good for some, it's not good for all. And in the HPC case, Singularity does not use the default runtime environment, which is based on Linux namespaces. So Linux namespaces have some good properties, like they reach very good density, for instance, but they have some drawbacks. One drawback is that they are based on a shared kernel, a single kernel instance with a pretty large surface of attack, which is exposed to all the application and is difficult to secure. With Meltdown and Spectre, it's actually becoming much harder. So this is a well-known issue in the industry, and there are a number of recommendations on how to fix this problem, but it's pretty difficult. So this white paper, which I recommend to read, is very long, but it makes a number of recommendations, starting from Second NSC Linux, custom kernel build, jar security patches. There are a number of them. But the bottom line is, it's difficult to secure the interface, and it requires detailed knowledge of the applications running inside, and at the end of the day, virtualization is still recommended. What I said so far is true about all environments, from data center to IoT, everything. But there are some IoT-specific issues that we have. Like, the most common scenario in IoT is a mixed criticality scenario. This is where you have a very critical application, usually on an RTOS, running alongside a far less critical workload. And what you need to ensure is that a crash in the Android, the non-safety critical workload, doesn't affect the rest of the system. So you need a fully fault-tolerant deployment. And this is not something you can do with Linux containers. So you need to be able to enforce that the memory that the RTOS needs is there all the time. And the RQ latency that the RTOS needs to function is also guaranteed. And that's not, again, something that can be done easily with Linux namespaces. And then there is the old can of worm that is certifications. Because certifications are very hard to do all the time. But if the code base is larger, they become extremely difficult. So you want a small code base if you need certifications. So the bottom line is, it would be great to have Docker as a packaging and delivery mechanism for your app, but then use something like Xen as your runtime for the applications. And this is what ViryaOS, which is this new Xen Project subproject idea, is about. The other problem that we are trying to solve, and let's step back from the world of containers for a second. Let's suppose that we are working, even just a couple of years ago, on a hypervisor-based solution for embedded, for example, set-top boxes. So you're likely going to have to build Xen, dom0, a couple of VMs, right? Otherwise, you wouldn't use an hypervisor if you didn't have VMs. That means you need to deal with a number of different build systems, produce the output of all the VMs, assemble all the output in a final image, pre-configure the image with device assignment, and to boot everything at the right time, and also manage software updates for your VMs and your system. So if it wasn't clear by my explanation, it's really a lot of work. It is. And when you think it's a lot of work, you haven't even realized that to have a more secure system, you need to disaggregate dom0 to even go further in fault tolerance. And this is where it actually becomes a nightmare. So what is the current state of things? Everybody has his own set of scripts, mostly bash, poorly maintained, poor quality, that are targeted at a single vertical, single board, and every time they need to switch, have a new project, work on a different board, or a different vertical, they need to do it all over. This is another area where ViryaOS will help. This is a proposal for a new Xen Project subproject. The idea is to produce a secure Xen-based runtime. So it's a ready-to-use image that you write to your SD card, you boot on your embedded board, and contains everything you need auto-configured. And it will allow you to deploy new application via Kubernetes, for example. These containers will be run as secure VMs out of the box. So this is a visualization of the build and the runtime. So the build tools will allow you to include your own user application, produce an image, you write to the SD card. It comes with everything you need to deploy at runtime containers as secure VMs. So we said dynamically deploy containers and VM both. So the technology to run containers as VMs, I can deep dive into it separately with you guys, but you can take Kata container as a reference. Here I'm going to show a demo based on Rocket and Stage 1 Xen. But there are a number of ways to run container application as VMs today. We want to do measure boot. It's not available today, but that's the intention. Software updates, obviously, are very important. System software updates and application updates. And disaggregation. What do I mean by that? So if you think as the simplest possible way to do this, you're going to have Xen, dom0, and a secure container runtime, which today is Rocket, tomorrow could be Kata containers. And then new containers get deployed as separate VMs here. OK, sounds good, right? But to actually have a secure solution with a decent level of fault isolation, you want to move the secure container runtime on a separate VM so that dom0 doesn't even have network access. So from the outside, you can't talk to anything privileged in the system anymore. Again, if this crashes or is compromised, it cannot affect the existing, it cannot affect the existing applications. You can take it one step further. You can separate the network stack in a network driver domain or network manager here. I have a domain that is dealing with the TPM and verifying not just the boot, but also container at runtime, their signatures, and the domain manager all on separate VMs. Now, this sounds like a good idea, but then, as you can see, you need to have a build of Xen, dom0, and at least 2 or 3 additional VMs. This is problem number 2. So this is why, when we started this project, we thought about the build quite hard. And we wanted to come up with a solution that wasn't useful, not just for Virya, but also to solve the larger issue of multi-domain builds. And this is how we are solving it. Each domain is built on a separate container. So these white boxes are separate containers. So for example, we are going to build dom0 with using Alpine Linux tools. We are going to use, for the additional domain, Yocto. Then the output of each of these builds, these are intermediate outputs only. In the case of Alpine Linux, they're going to be APKs. In the case of Yocto, it's going to be a rootfs. These intermediate outputs are given to another component, which is called image builder, which take all of them and assemble the final image, pre-configuring device assignment as needed. Now, here we went even to the length of separating the build of the dom0 kernel, which is in fact based on Yocto, from the dom0 rootfs, which is based on Alpine Linux. Why Yocto for the kernel? Well, because Yocto has excellent kernel support for embedded. It's the best out there. So we wanted to use that. At the same time, Alpine Linux is great, is small, has a lot of packages, is well maintained, is a great choice for the rootfs. So this build system allows you to mix and match different build systems to produce a single runnable image. Another point to realize here is these 4 intermediate output blue boxes are actually themselves containers. So what I mean is that these APKs are APKs in a container. And this rootfs is a rootfs in a container. Why? Because then you can push them all to the Docker Hub. It becomes an automatic backup solution. And also, if you as a user, you just want to add one component, you can pull all these intermediate outputs from the Docker Hub, and you don't need to rebuild them anymore. You only need to run image builder at the end. And this is what I want to show you now. So we support everything as a container. We support native builds, cross-building ARM64 using QEMU user. So that allows you to build stuff on your x86 laptop. And the rest I pretty much covered. So it's very early days, it's experimental, and we have a temporary mailing list, no official company support yet, so if you want to engage and help us out, let me know. And I'm going to try to show you a demo now. So this is image builder. That's the component that assembles the final image together. I just ran the Docker build for producing the container of image builder, which itself is based on Alpine Linux at the moment. This is done with QEMU user on an x86 machine, so it's a bit slow. As you can see, there is image builder over there. And what I'm going to do now is follow the README and run the Docker run command to actually trigger the execution of the image. So if you know anything about Docker, these two steps could be easily merged into one, but we are keeping them separate because it's actually easier as a developer to do them separately, I think, at least for me. All right, so this is a process, again, using QEMU user, so it's emulation of user space, so it's kind of slow on an x86 machine to produce a final image for QEMU. So we are going to have an image builder per target. At the moment, the first one we did is a QEMU system AR64 emulator. So this is going to produce a runnable image for QEMU with Xen and Rocket. At the moment, it's adding Rocket to it, setting up the partition tables. And now I'm just I'm copying the image to the location where I have the script to run it using QEMU, and I'm going to run it for you here. OK, QEMU is starting up. I'm using Tiano Core in this example, which is not super fast, but here you go. It's going to start Xen. Xen is booting. Then there's going to be dom0 booting. Everything will be configured out of the box. And what I want to show you here is actually Rocket is going to be able to deploy containers pulled dynamically from the Docker Hub as VM automatically, without any need for additional configuration. As you can see, well, the rootfs here is based on Alpine Linux. If you dig more into it, you see that the kernel is based on Yocto. OK, so dom0 is booting. And again, keep in mind, this is full emulation based on QEMU on an x86 laptop like this, which is not super fast. So as a matter of fact, now I'm going to start the Rocket command, which is itself written in Go. So it's going to look like time slowed down when you run it. But I assure you that when you run it, OK, so we'll see here that there is dom0 running, right? This is the command to run Rocket. Rocket run, insecure option is because Rocket doesn't do signature verification from container from the Docker Hub. Interactive, stage 1 then it was specified to run containers securely as VMs. And then Docker / ARM64 busybox, just as an example. Note that at this point, Xen has not even been invoked yet. Okay? This knowness is all Golang and QEMU so far. So the container has been pulled. And soon you'll see that Xen will start a new VM for busybox. This process on a real hardware takes about 3-4 seconds overall. It's just, I told you, in emulation is very slow. But has a benefit that you can test it very easily on your laptops. OK, at this point, the container has been unpacked, and we are going to start a VM inside QEMU. This is a busybox VM, and that busybox. So the only thing I'm going to show you now is I go back to the host, and if you look, there is a VM. But if you look at the Rocket list, there is also a container. That's because they are one and the same. And as you can see, the process is completely transparent. So as a customer or as a user, you can take any container, ideally, from the Docker Hub and deploy it automatically on your host as separate VMs. And that's the end of my presentation. So if you have any questions, please reach out to me. I'm here until Friday, and I'm happy to give you detailed live demo and deep dive into the details of these projects. Questions? Thank you. Microphone for the questions?
So you mentioned that you are doing some certifications, right, and using the PRK tool.
Yeah.
What certifications are you doing?
So actually, to be clear, I don't want to create false expectation. We are aiming at solving certifications. So we are aiming at ISO 26262 ASIL B, initially at least. That's what we are trying to go for. Now, the path is long, so it's going to be a step at a time. But yes, that's what we're aiming at. And the process would be to first make the code base as certifiable and as ready for certification as possible, and in parallel discuss how to produce these artifacts for certification out of the project, or at least store some of them as part of the project, to make it as easy as possible for companies to do the certifications themselves. And ideally, potentially even do the certification as part of Xen Project, but it's kind of a stretch goal. Other questions? All right, if there are no questions, and that the time is out, so thank you very much for attending.